Sorry, new to Teams, absolutely terrifying. This is the most social interaction I've had in months. That's cool. Um, so yeah, I'm a physics person, but I'm not gonna be too annoying about it today. I'm gonna talk about something I haven't a clue about, or at least I didn't until a week ago, and that is if you wanted to stop a hurricane, how would you do it? And then with a kind of an undertone of complexity in physics, so I can feel good about myself. Right. So here's the plan. We're going to ask, what's a hurricane? Where is it? Why does it happen at all? And then how do you kill it? Or is that possible at all? So step one, what's a hurricane? Well, it's a big, windy, spinny boy. I'll get a pointer here. It's absolutely massive. It's full of energy and power, and it destroys a lot of the coastal cities of places like the south end of North America here. And we call it a hurricane if it's over here. We call it a cyclone if it's down here, and we call it a typhoon if it's up here. They're all exactly the same thing. And the reason I used hurricane in the title is because of, I don't know, USA-centric bias. And then how we classify them, and you might have heard about a category 1, 2, 3, 4, or 5 hurricane, is just about if it can sustain a wind speed of mental numbers, then you just give it a number according to that. It's theorized that there's no such thing as a category 6 and that it can't get higher than this. Although some people think that with climate change, it actually can get worse, but we'll find out. Here's some fun facts about hurricanes. They're some of the most lethal and expensive natural disasters ever. Katrina, Andrew, and Harvey were all in the tens or hundreds of billions. A single cyclone in Bola killed nearly 500,000 people. That's not necessarily a fun fact, but it does demonstrate the power that's going on there. Yeah, they have to start to be called a hurricane. It has to have sustained winds of 33 meters per second, which is, I think, like twice or 3 times as fast as Usain Bolt can run. It's often recorded by absolute insane people who fly planes directly into them, and that's how data has been recorded for a long time, which I couldn't believe when I read the first time. There's a hurricane on Jupiter, and you could fit Earth in it. There it is there. It's the big red dot on Jupiter. It's actually just a massive hurricane. You could, for a typical big one, you could fit Ireland in it 70 times. That's how big they are, or at least in terms of the cloud cover. And we usually give the big ones names so that, like a pet, we're sad when they die. I think it kind of takes away the sting a bit. So now let's find out how they form. Where do they come from? Let's say you're out in the ocean. The water is warm, 26 degrees or higher. So this only happens in certain parts of the world. But let's say you got a nice warm ocean. You have winds that blow across the surface, and it starts to interact with the boundary layer here. Heat and water will go from the ocean up into the air with, like, waves and things interacting with the boundary. Since the warm air, since the air heats up, it becomes warm. Hot air rises, like from a radiator or something, goes up. It leaves a low pressure area behind and a high pressure area where it goes to. This warm air, once it gets up here, kind of like if you took a garden hose, and you pointed it straight up, it would just kind of mushroom out at the top. That's exactly what happens here. The cold air just kind of goes out to the sides and starts to fall back down again. And there's an area in the middle where it's kind of like stagnant a bit. It falls down to the bottom. There's a low pressure area here. High pressure air wants to go into the low pressure area, so it starts to go back to the center. As it's crossing the water again, it picks up more heat, and what you have is a big scary cycle. And it just keeps picking up heat and more energy and more energy and more energy until it's completely massive. In the middle here, you have this little area of stagnation where it doesn't really know whether to go left or right or back or forwards. And so what can happen is it can start falling back down again, and you reach like a bit of an equilibrium where you've warm air that's kind of going up on the sides, and then in the middle it stays low pressure and it stays kind of cold. And if you remember that clouds are just kind of cool condensed air, it's easy to see why these areas up here would be just covered in clouds. You wouldn't really be able to see through them because the water vapor that's in the air has condensed up here, so you can't see it through it anymore. And in the center here, what we have is a low pressure area where there's no clouds, and that is what we call the eye. There's a big hole right in the center of a hurricane, and you can usually see right through it. Sometimes, like down here, there is you can fit like a whole country or an island in the middle, like that's Barbados there. So they were hit by unbelievable winds, and then briefly it was fine and quite nice, and then it was terrible again. So then the eye is quite a weird one. It can look kind of funky like this. So you can kind of see there's like a pentagon thing happening here. It turns out it's very complicated in there, and it's actually similar physics to the kind of insane hexagon that you see on the North Pole of Saturn, which people didn't understand for a long time, but we do now. And it's pretty much the same physics that makes a weird like pentagon show up in some of the eyes of hurricanes. And so what we get in the end then, instead of one big cycle that just happens like this, you get smaller cycles where air goes up and it falls down here, and it also falls down here and here, and you get these little mini cycles, and that's what forms the like band structure, and why it seems like it's like a spiral. You get these little bands of clouds. Since the warm water is the fuel for the hurricane, that's where it really gets its energy from. A lot of people think that climate change, since the ocean temperature is going to increase, is going to make the intensity of hurricanes worse and also the frequency higher. Fortunately, it looks like the literature suggests that it actually won't get much worse. In fact, it might get better for the next 50 to 100 years. There will be less hurricanes, and then it'll get way, way worse, but we'll all be dead, so it doesn't really matter. Cool. So where do they happen? Up here for us in Ireland, up there, there's not really much. But you can see that in this band here and in this band here, just near the equator, you get loads of hurricanes starting. And that's because this is where waters are warm, and it's perfect conditions for this low pressure thing that I talked about. And what happens is they start down here near the equator, and then they start to curve up towards the North and the South Pole. And they don't make it very far before I say they don't make it very far. They can make it very far, but if they hit land, they tend to die off fairly quickly because their fuel is gone. Is it possible to stop one of these? Well, probably not, but we'll do some science. In general, I think this is how science should be done. You start with a cool idea, you realize it's hard, and then you pretend it's easy. That's what we call assumptions. You get a very nice answer, but it's completely wrong, and that's fine, because you can start to peel away the terrible onion of wrong you've made, and then you realize it's hard again when you try to do that, and that's why you pretended it was easy in the first place. So you just pretend that the assumptions are justified. You can delude yourself into believing your own callous lies, and then hope no one notices. Oh, sorry, this shouldn't be. Oh, sorry, this is the wrong slide. Yeah, there you go. So you can publish your results, and then peer review happens, unfortunately, and then someone realizes that you messed up. But you can just change your conclusion to say that the results are inconclusive, and then it's fine, and you can publish your results. Cool, and that's science. So we have our cool idea, and that is, you have a hurricane, and you want to stop it. Let's say we stick a bunch of wind turbines into it, and we see how long it takes before it takes all the energy out. It is now time to realize that that's hard, because we need to work out how much energy is in the hurricane first. So we'll look at the kinetic energy of the air only, no potential energy nonsense. So it's as simple as, for every single molecule in the hurricane, you add up a half mv squared. That's the total energy then. The problem is that this speed here, and also the number density of molecules, varies in every direction. So this is cylindrical coordinates here. It'll vary radially, it'll vary as you spin around, and it'll vary along the z-axis, because these things are up to 16 kilometers high. So there is a huge temperature difference between 16 kilometers up and down here. And so we don't even know how to calculate the number of particles that are there. And so this kind of estimate is going to be difficult to do if we're doing it accurately. So we pretend that it's easy, and we pretend nothing varies. And let's say the speed, the pressure, temperature, everything, all that, it's all constant. So we can do a simple leaving cert ideal gas law sort of thing. We'll look up some numbers for a particular hurricane. I did it for Hurricane Tracy. We'll plug in the numbers. And what we get when you plug in some simple numbers, and this is the ideal gas law coming in here, is about 140 terajoules. And that's a very big number. That means that just in the kinetic energy of the spinning, not even the vertical motion, that is 2 times the energy of the bomb named Little Boy that was dropped on Hiroshima. So that's quite a lot already, and we're missing a lot of the energy there. So that's, it's worrying, and it doesn't bode well. So now that we have our very nice, very wrong answer, it's time to peel away some of the wrongness layers. So layer peeling step one is to recognize that the velocity doesn't just stay constant. It starts in the eye of the storm really low, and then it starts to get really, really fast, and then it dies off. So this axis down here is the distance away from the center, distance away from the eye. This one here is the pressure, and you can see that the pressure starts really low as well, and then it goes crazy. These are analytical models. These are equations that I stole from a paper from 1980. And yeah, so this orange one here corresponds to the pressure, and this one to the velocity. And just to prove that this is a reasonable thing to do, this is a comparison with Hurricane Tracy here. That's Hurricane Tracy's data, and you can see it pretty much fits. This is a bit messier because it was recorded by a man in a plane, but it fits pretty well. So we're going to use these as our speed and pressure. So previously we had this, but now our ideal gas law is a bit crazier. This is a bunch of maths that I'm going to skip because no one cares. There's cylinders, there's differentials, and there's complicated expressions. And then you put it all in a computer and it gives you a number, and you forget about all the hard work. And the answer you get is about 120 terajoules. So we were overestimating a little bit before, but it's still pretty much twice the bomb energy from before. So it's still a huge number. So now we need to realize that there are much more wrongness layers to peel back, and I've given them a go, and it was impossible because to account for the fact that it varies vertically as well as radially, you would have to do like a big crazy integral, so I didn't want to do that. There's loads of humidity in the air, and that has loads of potential energy, like the latent heat of water and all this, not accounting for that. Coriolis force, the temperature is constant, but it isn't. The hurricane actually has a track, so it is moving as a whole. Didn't account for that. When the water in the air condenses, you can't even call it an ideal gas anymore. So even though the number I got there is actually pretty close, there's a lot of effects that aren't being taken into account. But luckily, I kind of checked them. They were of an order that isn't too big of a deal. So we're just going to pretend that our assumptions are justified. All good. Use our number. And we've successfully deluded ourselves so that we believe it's fine. And now we're going to stop Tracy. So what if we just sucked up all the energy with wind turbines? Surely that would work. You just put a big wind turbine farm out in the ocean, and then we can take all the energy away instantly almost. Well, so we'll do a quick math check. The most recent big scary turbines are the Haliade X or something, and these are 12 megawatt offshore turbines. And now in the previous talk there was mentions of like kilowatts, and you heard about how insane a kilowatt was in terms of the energy. So these are megawatts, which is 1,000 times more, and that is the power output of well, not one of these, but a much bigger one. They cost 400 million each. This is in the wrong order because I made this recently. Yeah, so if Tracy has 100 terajoules, then this is our guess here. We got 120, but we'll say 100. Then this math over here from a different paper, which actually isn't too complicated, but I don't want to get into it, tells you the rate of power loss to friction. So what you get is that there are roughly 3 terawatts, which is 3 million watts is the amount of energy that it both loses through friction and gains from the ocean if it's in the steady state. So that's a huge number, and you would need about 250,000 of these very expensive $400 million turbines to take care of that. That said, to pay for that, you would need $100 trillion, which I thought was a lot at first, but the US national debt is 20 trillion. So it's really not that inaccessible. Not only this, but you would be saving billions on hurricane damage. And as well as that, they use about 1 million terajoules of energy in a year. So you would save about 500 billion on energy costs. The problem is it's a difficult one, and so I can't do it on my own. And so I turned to a paper in Nature where a very smart man at Stanford did calculations with these things here, which I don't understand, but they're these huge supercomputer models. And he modeled what you would need, or how many of these turbines you would need to reduce the speed of the hurricane as opposed to delete it completely. He found that 70,000 turbines would actually reduce the speeds by 41 meters per second. And this is great because the damage a hurricane does it goes as the cube of the speed. So if you reduce it by 41 meters per second, you're actually reducing the damage by like 41 cubed. The storm surges, which is the water that a hurricane takes with it, would be almost completely eradicated. Great. In the end, when you take everything into account, and he really did take everything into account, you would actually produce cheaper energy than fossil fuel burning, which is great. The problem is that they're inconsistent. They don't show up super often, maybe like 8 per year in the States. And so you would have to store the energy somewhere. But battery technology isn't great yet, so we have to rely on some intelligent, maybe not, people to make better batteries for us so we can actually store the energy. So until then, that's a pretty major engineering problem for absorbing this energy and putting it somewhere. Some people have said you can dump the energy somewhere else in the sea, but that's stupid because then another hurricane would happen over there. There is another problem, which is that, as I said, through friction, it loses about 3 terawatts. So this is 3 by 10 to the 12 joules per second. But we found that...
Ian, I'm just going to give you a 3-minute warning
Cool.
just for the talk. Thanks.
That would mean that since we found 100 terajoules of energy in the rotation, it should go away in a few minutes. So we must be missing a bunch of energy, and it turns out we are. The amount of energy in the latent heat of water in the moisture in the air is actually 400 times more than the energy of it spinning. And so in reality, there is this huge source of energy so that it doesn't actually dissipate in a few minutes. It does stick around. And when it hits land, it doesn't disappear straight away. It kind of keeps chugging along using this latent heat of water energy. And so really, a hurricane is not 2 of those bombs. It is 800. And there's lots of different numbers you'll find on the internet. Like, a hurricane is this many nuclear bombs. This is about as accurate as any of them. They're all huge approximations because hurricanes vary a lot. There can be an order of 10 in the difference between 2 given hurricanes. So people have had ideas other than the wind turbines. For example, could you nuke it? The National Oceanic and Atmospheric Administration says, needless to say, this is not a good idea. They go on to explain why it isn't a good idea, but I feel like it should be fairly obvious. There is one man who seems to think that this is a great idea. And the quote is, I got it. Why don't we nuke them? I love the confidence, but nothing is better for a hurricane than a huge pressure differential and adding loads and loads of energy into it. So yeah, we'll not do that. That's a bad plan. We could try and take away the fuel. If the fuel is hot water, Bill Gates was part of funding an idea that would kind of like take the hot water near the surface, suck it down through a big tube, and then cold water would rise up to take its place, and this would remove the fuel source for the hurricane when it's forming. The problem is that it would likely wreak havoc on the ocean currents that are pretty vitally important to the climate already. And so this was largely ignored, and I think Bill Gates has given up on it himself. But it was a nice idea, I think. So here's a summary of the options here. Turbines, cheap, clean energy, that fits in with the last talk. There's a connection. And it can also significantly reduce the damage in a really major way, because people do have their lives ruined by this kind of stuff in the thousands, or even the hundreds of thousands. But the problem is that there's an absolutely insane startup cost, and some of them just break in a really big hurricane. But you can fix this by programming them to turn away from the wind if they're being damaged. So that's not too big of a problem. Nukes intimidate Korea, great. And you finally get to press the big red button that he's been wanting to press this whole time, but you would blow nuclear fallout all over your own country, and you'd probably make the hurricane bigger. So that's not great. And then the water cycling might prevent hurricane formation, but the fish would not be happy, and probably neither would the weather systems in other parts of the world. And then that would eventually come back to bite us in the ass anyway. And so the conclusion is, don't fight it. Drop your wallet, run. It's not worth it. You're not going to kill it. It's too big and strong. And so, yeah, I think that's everything.
Okay, well, thanks, Cian, for your talk. I really learned a lot, and it was really funny as well. So if anyone wants to join me in a round of applause, does that work on Teams?
I don't know. Yes, I can't see anyone, but I'm hearing effort. Thank you so much.
Brilliant. So do we have any questions?
Yeah, any
questions? If anyone has a question, just put it into the chat or voice if you want.
Oh yeah, I'll. This is gonna look weird for a minute while I look at the chat. Wugo, thanks, Rory. He's a good lad. I did do, in case no one has a question, which is fine because I wouldn't either. I did do a slide on why does it spin? Because in the southern hemisphere it does a weirdness where it spins in one direction, and in the northern hemisphere it spins in the other.
We have a question.
We have a question. Where is it? Let's see. No, I've been reading about hurricanes more than other things in my life for a couple of weeks now, and it's been a nightmare, and now I hate them. But I made the presentation in maybe like 3 or 4 days. But yeah, I can basically, if in case you don't know what the Coriolis effect is, that's what causes it. Or sorry, if in case you do know what the Coriolis effect is, that's what causes the different spin in the different hemispheres, because as the wind is going towards the low pressure area, it gets deflected, and the deflection causes it to spin. I did a slide on how the Coriolis effect works, but I don't think it's I don't think we need to go into it. Let's see. 32. You know, I was not sure if I wanted to include that picture in it, because it did look like I did it myself. But no, that picture of that family, we'll go to the slide. It's 32 or 30, this one here. So this family up here, I found that this like cut out picture of them is for some reason like superimposed onto lots of different stock photos of wind turbines. And so I spent a lot of time trying to work out which one was the best one, and I settled on that one. I think it was a reasonable choice.
I actually have a question as well. So you mentioned about the wind turbines, but like how big of an area would you need to cover like to stop, say, the major hurricanes that cause all the damage?
Well, 70,000 of them. Thanks,
Yeah.
Rory. 70,000 of them. They are something like 100 meters across or something, and you wouldn't want to put them too close together. So it would be covering an area of ocean that is like kind of unfathomable. I couldn't even give you a number, but it's 70,000 times, we'll say, 100 kilometers squared, something like that. And so yeah, it's an absolutely massive area, and obviously that's why it would cost so much. Riffing off Trump's idea, what if you built? Well, yeah, that's a seawall. Yes, they do. So okay, so David's one first. Seawalls are a thing that were considered in that Nature paper I was on about. The guy who did the big simulations, he also simulated seawalls to see if they were more cost effective, and they don't help with the wind as much, but they do help with the huge storm surges that actually cause most of the damage. But he found that they would end up being more expensive. It would be more expensive to build the big seawalls and maintain them than it would the turbines, and also you wouldn't get clean energy out of it. So he decided that this was worse, and I'm inclined to agree. Wind turbines do have a max speed. The one that I was talking about, the 12 megawatt whatever, this one it doesn't respond well to speeds that high. So basically, you would have to. This was used as an estimate of the maximum power output of one of them, but it would be an engineering challenge basically to work out how to make turbines that have a speed response or like a power response that is more peaked in the like 33 to 50 meters per second range. And then once that was done, it would be more effective at soaking up hurricane energy. But yeah, currently the turbines we have wouldn't be great at this task.
Okay. So if there's no more questions, I think we'll leave it there. So thanks very much, Cian, for speaking and for putting together the presentation. It was brilliant.
Cool. Thank you.
Thanks so much, Cian.
No bods.
Thank you, Cian. I love your work.
Thank you.